Hi, my name is Nils, and I come from the Swedish professional services company Meraton, and I'll talk about a memory adventure called Dude, Where's the ROM? As we all know, the ROM is gone. I tried to find it, and it was harder than I expected. So the first image is just a stack trace that you've all seen, and this is extra good because it doesn't even have the starlark stack trace. It's just a Java heap space error. But even if it did have the starlark stack trace to identify the culprit, with memory, whatever fails may not even be the culprit. So I have a diagram there with a green allocation that fails. But the big problem is the larger red box below, which would not be identified by a stack trace. So we start with some synthetic data to figure the problems and see what tools can help identify it. So we have a basic CodeGen repository with Python and C++ code. And then I added two aspects. One is very memory intensive, that encodes a string of the dependency tree for all targets and allocates more and more and more. And then there is a CPU intensive task to model the water, which actually allocates a lot in the build phase, but not in the analysis phase. So we have a catalog of tools. Many of them are post hoc, and these are what the guide for memory analysis talks most about. We have Bazel info, Bazel dump, and we have the A query for sky frame state. Then there are the Java tools to understand what the Java process does, with the Eclipse memory analyzer being very good. And you can also dump a histogram with JMap. And we also did some work with the Bazel profile, which is customarily used for CPU profiling, and it has the well-known Chrome tracing format, and it can easily be parsed. And to restate it, our problem is that the analysis phase is on the critical path for all builds, especially when you use remote execution and remote cache, and you don't want to execute any actions. And in our specific example, we have very large action objects. So Bazel dump rules doesn't work. Here is the result. It's hard to see, but it's not at all close. So we have up to 17 megabyte large strings in the memory intensive aspect, but the profiler says that it's about 14K or 4K each, which is not correct. The Eclipse memory analyzer is much better. It even finds our big string that's 17 megabytes. And it comes from a configured aspect in a skyframe executor. But we don't know which skyframe executor. We don't know which starlark, which function. But a heap dump can tell us the problem, just not where the problem is. And we did plot the memory or the execution time against the memory limit. So when you vary the memory limit, it starts to fail with low memory, and then the time increases until it reaches a transition period where it sometimes fails and sometimes does not fail. So there are some crosses and a success, and then more crosses, whereas at least one run failed at a given memory. And then it flatlines with constant performance. But if we enable SkyMud, it looks very funny in the low memory region because it tries even harder and does more, manages to do so before it fails. But at some point it starts to succeed, and then it requires much less memory because the resident set of actions to execute can be worked off, or you start to work on action as soon as they're analyzed, and then you can free the memory much sooner. You don't need as much at any one point. And we also notice a plateau, which is thankfully highlighted by the screen limit here, that it goes above, up to the third screen with medium memory, and then it falls down to a flat line, which is actually less memory or less execution time. So we find that there is both a region where it crashes, but also a pessimized plateau with barely enough memory, where more memory will make it faster, but enough memory still works. And this is also very hard to diagnose without just trying with more memory. Yeah, these are the points. And we also have some speculative ideas about looking at the profile for the active threads at the time of the crash. That the problem should be statistically overrepresented very close to the crash if we parse the profile. And we can also parse all the events and functions and compare them against the number of garbage collection events. The more garbage collection events concurrent to any function evaluation, the higher the risk that it's at fault. And you can also notice in this, I don't have good slides for it, but that we see restarts of the starlark functions. So the less memory, the more often any given function is called, presumably because it's restarted. And then you can also look for the cause in the statistical patterns. So our takeaways is that we don't have a solution. We don't know how to find the memory thief, but we think. And we tried to create a big, hairy code base, which was, well, that we can do, but it's not representative of large corporate code bases. And the analysis tools each have their pros and cons. But we think that if you can profile a lot and save them within CI and go back and analyze what's different in the patterns between successful builds and crashes, that may be very useful. And we have our example repository with aspects to do stupid stuff on GitHub, Marathon, and Memory Adventure. And we'll write blog posts with deeper analysis as we perform them. Thank you.